Hello students, welcome to lecture 8, chapter 1, Fundamentals of Design. In this lecture, today we will discuss about standardization, advantages of standardization, preferred number series, theories of elastic failures in detail. So let us see one by one all points. What is standardization? It is the process of establishing standards. Why we are establishing standards? To minimize the variations, or we can say to minimize the varieties in the characteristics. Like we might have seen certain symbols, traffic symbols on road. They are standardized symbols which are universally accepted. Similar to that, you have studied symbols for materials, conventional representation symbols for machine components like bearing. Everyone will understand that symbol. If bearing symbol is drawn, it will be interpreted in the same way. So what is the purpose of standardization? We have to establish the norms to achieve uniformity. Uniformity means everyone will interpret and understand it in the same way. Whenever we are following standardization, there is a minimum specified certain quality level. Interchangeability, safety, and we are putting a reasonable limit to the varieties of the product. That is the purpose of standardization. Now, which are various standards used in design? First is standards for materials, mechanical properties and chemical composition. I told you standards for materials. Right now we have seen commercial designation of the materials. I had explained in the last lecture. 40C8 means everyone will understand that it is a carbon steel with 0.40% carbon and 0.8% manganese. So we can say that is a standard for material. Then there are standards for mechanical properties. If I am writing BHN 300, that means it is a Brinell hardness number. Similar to that, there are other mechanical or other properties also that will be everywhere uniformly accepted. So that are standards for mechanical properties. Standards for chemical compositions. Chemical composition means what? How much is the alloying element? For example, we have seen a designation of the material. First is a figure 100 times average percentage of carbon, followed by chemical symbol of each element, like in a commercial designation of material. So here these are standards for material which will be accepted, and that is varying. Those standards will vary. Like you all must be knowing, there are other standards also which we will see after this slide. There are standards for dimensions commonly used in machine elements. Standard for dimensions means there is a method of unilateral or unidirectional dimensions. Radial dimensions are also there. There is a specific technique for dimensioning in the drawing which are used for the commonly used machine parts. And third is the standard for limits, fits, tolerances and surface finish of machine elements. Limit means in which range our components basic size is going to vary. We can allow that basic size to vary between which two extremities, that is a limit. Degree of tightness or looseness is known as a fit. Tolerance is the differentiation between the maximum and minimum possible limits. So we have this standardization for all this. We have surface finishing symbols like 2 triangles, 3 triangles starting from N1, N7, N8 grades. If I'll say that it is 50H7G6, H is a capital. So 50 is a basic size, H is the whole basis system, 7 is a tolerance grade, small g stands for a type of a shaft, and 6 is the tolerance grade for shaft. So interpretation will be done same way by everyone. Last is the standards for engineering drawing of components. Standards for engineering drawing of components will be, there are standards like maybe first angle projection method, third angle projection method. So which view will be where with respect to XY line, with respect to front view, top view, side view will be where. That is also, we can say, standardized pattern. In drawing, if we take an example of production drawing, what is a standard in the production drawing? We need to show on a component drawing, we have to show machining symbols, surface finishing symbols. We have to even show that material removal is required or not required. So these are all known as the engineering drawing components standards. Next, I was talking about the standards which we know that are common standards. There are either international standards, national standards, company standards, or local standards. For example, IOWM, International Organization for Weight and Measures, that is international standard. BIS, Bureau of Indian Standard, is a national standard. Like that way, there are certain standards which are designated by the company itself. Few companies, you can say group of companies will decide a standard, then it is known as company standard. And again on a lower side, if next standard we see, that is a local standard. Now we will see advantages of standardization. How it is helpful in the industry. It helps to manufacture the components quickly and economically. Because here standardized manufacturing methods are used, processes are standardized, planning is perfect. So manufacturing of the component will be quick without wastage of much time, and it will also reduce scrap, rejections, wastage of time also will be less. So component will also be economical to us. There are certain components which are readily available in the market, and there are certain designs also which are made by the experts. Readily designed components are there by the experts. So if we are directly taking those components and we are following those design, like design of gears, a standard method is available. Design of bearings, rolling contact bearings, sliding contact bearing, a specific method is available. So we can save the efforts because those standard designs are readily available, and we can adapt those designs with our values. We need to apply it. Third advantage is it helps in manufacturing the components on a mass production. Whenever we are using standardizations, our methodologies are standardized, plant layout is standardized, machineries are also as per the standards. So, and there will be a better utilization of resources also, you can see here. So efficiency of all resources will be higher. Not only man, material, machineries, all will be utilized properly, and a company can have the facility of mass production if they are using the standardizations in each and every aspect. Next is the interchangeability. When any company is following standardization, they are following a uniform method of manufacturing, and they have tighter tolerances of the components. And those tighter tolerances component, with that possibility, we can replace X company's product with the Y company's product, which is known as interchangeability. For example, we are having a nut. First, we have fit that nut in a X company's bolt. Now that bolt is worn out, so we are changing the bolt, but now we are fitting Y company bolt. So we can say here this facility is interchangeability because nut is manufactured with the standard dimensions. So any company's bolt can be assembled with that. Whenever standardizations are followed, students, It ensures that a company is maintaining a minimum specified level of the quality. Minimum. I am not talking about that company is maintaining 100% quality. Minimum quality can be 90%, 95%, can be 98% also. But company can give assurity to their customers about certain level of the quality. Whenever there is a standardization in the industry, all resources will be properly utilized. There is effective utilization of the resources, which I said before 2 minutes. It makes easy and quick replacement of the components. Whenever there is a standardization, whenever you are dismantling the components during servicing or maintenance, after servicing and maintenance, replacement of the components would be quick and easy. And standardization also ensures safety of the operators, protection from the hazards and accidents. Even environment also would be safe. So here, these are all advantages of the standardization. Next topic today which we are going to discuss, that is preferred number series. That is for minimizing the variations. This number series which we will be using, like there will be S5 series, S10. S5 means 5th root of 10. S10 means 10th root of 10. S40 means 40th root of 10. So here these whatever are the answers of this 40th root of 10, 50th root, 80th root of 10, 20th root of 10, that value will be multiplied by the previous value to get the next size. Now that next size will become the previous size, then it will be multiplied by a multiplication factor. We will get a new size. Now that new size will be considered as a reference. That will be multiplied by the multiplication factor. So there is a geometrical progression with a constant ratio. So we will take an example of a component. You can see here these are the multiplication factor of S5, S10, S20, S40 and S80 series. So if we take an example of S5 series, if first size is 10 millimeter, second size will be 10 into 1.58. So approximately it will be equal to 16 millimeter. Then 16 will be that 15.8 also will be multiplied by 1.58. So it becomes around 22 point something. So next size which is rounded off will be 23 millimeter. Similar to that, if again we are multiplying it by certain value, then it becomes the next, it will give us the next value. So these are all the multiplication factors. If we are using S5 series, you can see multiplication factor is higher. So our steps are bigger, but the number of varieties are less. On the other side, if we are using S40 or S80, we can see multiplication factor is 1.06, which is too small. If first value is 10, second value will be 10.6, third value will be 11 point something, fourth value also will be 11 point something. So you can say that steps are very small, but the number of sizes available are large. So depends on our requirement, we need to select this preferred number series. It is applicable to the shaft sizes, maybe bolt sizes, maybe other type of sizes. So that is what is a preferred number series. Next in our syllabus, we are having theories of elastic failures. Now, whenever there is a uniaxial member, like a component is subjected to only tensile or maybe only shear, then its analysis would be very simple. But when a component is subjected to biaxial or triaxial stress system, its design will become more complicated. Sometimes the design is so complicated that we cannot solve it by the old method which we were following, that stress is equal to load upon area. For those complicated designs, new theories are developed, and those theories are known as theories of elastic failures. So we are having 5 theories of elastic failures. First is a maximum principle or normal stress theory, which is also known as Rankine's theory. Similarly, maximum shear stress theory, maximum principal strain theory, maximum strain energy theory, and maximum distortion energy theory. Here, we will study 2 theories today. These theories of elastic failures, we can see that in ductile material, it is subjected to yielding. Yielding means there is a deformation. But brittle material fails by fracture. There is no deformation. So here, limiting strength for these 2 classes of material is measured by the different mechanical properties. And prior also, in factor of safety topic, we have discussed that ductile material is having a limiting strength as yield point value or yield point stress. Okay, and brittle material is having a limiting strength, that is a ultimate stress, both in tension or compression. So here we will first see maximum principle or normal stress theory. Actually, in this theory, what is the theorem? That here any component is there which is subjected to biaxial stress system. Biaxial means the force is acting in X and Y direction both. So whenever there is a biaxial stress system, failure of that component will occur when its maximum principal or normal stress value will reach to the limiting strength of a material in simple tension test. So that theory is known as maximum principal or normal stress theory. Since limiting strength for ductile material is a yield point stress and for brittle material it is ultimate stress, so when we consider the factor of safety into consideration and we write the formula for our tensile or a normal stress, then the formula will be given as sigma YT upon factor of safety. This is yield point stress for ductile material. Sigma U upon factor of safety. This is ultimate stress for brittle material. As we have seen that maximum principal or normal stress theory is based on the failure in tension or compression. It ignores the failure by shear. So therefore this maximum normal or principal stress theory is not used for ductile materials, but it is preferable for brittle materials. So students, next theory which we have, that is maximum shear stress theory. Maximum shear stress theory, there is a material will be subjected to failure or yielding occurs at a point in a member when maximum shear stress in a biaxial stress system reaches to a value equal to shear stress at yield point in a simple tension test. That means a failure will occur when a maximum shear stress value will reach to a limiting value, which is shear stress at the yield point. And the stress system is a biaxial stress system and the test is a simple tension test. As per this theory, formula is tau max is equal to yield point shear stress upon factor of safety. As we know the relationship between yield shear and yield tension, yield shear is half of the yield tension. So we will substitute that value of tau YT as sigma YT by 2. So our formula will become tau max is equal to sigma YT upon 2 times factor of safety. Now we know that sigma YT upon factor of safety is sigma T1. So we can say that tau max is equal to sigma T1 by 2, or it is 0.5 times sigma T1. I hope you have understood and enjoyed all the topics which we have discussed today. Thank you very much, students.